ponds. I've got a note there under question 2 under the table that just says, note that sinuosity equals the channel length divided by the straight line length of the valley. All right, so what does that actually mean? Well, for a start, let's measure the length of the channel for this reach around where the dot is. So we can just use our measuring tool in Google Earth. Can you see that ruler tab that's appeared on the screen there? Okay, so we're going to measure. I've got the length in meters. It doesn't really matter. Kilometers is just as good. I've just got it set to a line. And now what I'm going to do is just trace the channel. Okay. Let's go. So oh, it's not doing that well. Hang on a second. Oh, I don't want it to be a line. I want it to be a path. Sorry. A path. And let's see if this works. Oh, clear that. Nope. Yeah, here we go. So I'm sort of following the channel. You can see it bends around a little bit. There's no channel through here, so we'll just keep going. Okay, and I'll end it there. So you can see on my measuring tool, that was 2.4 kilometers. I'll just write that down somewhere, 2.41 Ks. Now what we want to do is that's the length of the channel through that reach. Now what we want to do is work out the straight line length of the valley. So if we just clear that, now we do another line, but this time we're going just straight down. The straight line length that valley has there, and that is 2.04 kilometers. So the calculation we need to do here is the length of the channel divided by the length of the valley. So 2.41 divided by 2.04 equals a sinuosity of 1.18 or 1.2, just to make it simple. So if we come back into our worksheet here, the sinuosity of those chain of ponds was 1.2. Now the next thing we're going to look at is the meander wavelength. So the meander wavelength, I did have a good image of this, just let me find it very quickly. You can Google this as well. All right, copy the image. Now, I don't know where I can, I don't know if I can paste this in our chat. Anyway, here, I'll just share my screen for a second. Again, this is share Google. So you can see here, I've just Googled meander wavelength. What is it? Well, what we're looking at, if we look at this image here, is it's the distance between the apex of each meander bend as you move downstream. So this is called the meander wavelength. We're not interested in this case in meander amplitude. That's the width of the furthest meanders from each other. So meander wavelength is this distance between the edge of the edge of the meanders. So let's go back to sharing. Let's go to Google Earth and measure that distance if we can. All right. So there's not a lot of examples here of big meanders, but in this area down here, there's a couple of little bends. I mean, there's not many. What we could do is, for example, use, I mean, there's two here in a row, but we could basically go from there to there. And that distance is 240 meters, so 0.24 kilometers. So if we go back to our worksheet and fill that in, it was 0.24 or 240. I've asked for it in meters, so 240 meters, roughly. For this system, what are the indicators of channel instability? Well, the answer here is there's not many, but erosion occurs between the ponds. So really erosion, a little bit of erosion is the only indicator of channel instability in this system. The next question is, what's the planform type? And we already know that it's a chain of ponds. And actually, if we want to add any information to this, it's an unconfined alluvial chain of ponds. Unconfined valley, alluvial means it can rework itself if it wants, but this one doesn't have much chance, and chain of ponds because it's a discontinuous system. So I won't do number 2. Number 2 was the braided river. What I can tell you about number 2 is that don't bother calculating the meander wavelength because it doesn't meander. I can also tell you that sinuosity is 1. It doesn't have any sinuosity. It's a very, very straight river. So it's got 1 channel, sinuosity of 1, don't worry about meander wavelength, and the indicators of channel instability are that it can move its thalwigs and move its banks. So this is very similar information to what you had in the first table. Let's go to one of the more interesting ones. So we won't worry about the gorge right now. You can come back to that. Let's go to the discontinuous floodplain, so site number 4. I'll go back to Google Earth and find site number 4. I'm keeping my ruler tool up there because we're going to measure a few things here. All right, so this is the partly confined valley. Why is it partly confined with discontinuous floodplain? We can see the ridges here running along next to the river and the valley in between. And you can see these low-lying, see there's water sitting on the floodplain in that little light-coloured patch, and then there's a light-coloured patch here, another one here with water sitting in it again. So these little parts of the floodplain are not connected to each other. The channel bounces off the valley sides along here and leaves these little pockets of floodplain. That's why it's a discontinuous floodplain. But what we want to do here is assess how many channels. 1, that's pretty obvious. What's the sinuosity? Okay, so this river is running from up in the top of the screen down to the bottom in this case. So what we want to do is measure the sinuosity by measuring the distance downstream. So let's just pick a reach that's a little bit sinuous through here. Oh, let's clear that. It's trying to measure it from the last site we were at. Okay, so I'll start there, follow the channel. It's not the best channel mapping I've ever done, but you know, you get the gist. Okay, I'll stop there. So that's the reach we're interested in. The length there is 11.75 kilometres, according to Google Earth. Now we want to measure. I'm going to clear that. We're going to, well, you can show the elevation profile of that. You can see it's a bit dodgy because I was clicking fairly randomly. But anyway, what I now want to do is calculate the straight line distance between those points. So I'll clear that and I'll just go from there to there. That is 10.15 kilometres. So the calculation we want to do here is 11.75 kilometres of river length divided by 10.15 kilometres of valley length. That equals a sinuosity of 1.16. So let's go back to the worksheet. Where's the worksheet? Okay. So the sinuosity here, so 1 channel for the partly confined one. This is site number 4. Sinuosity was 1.16. So less sinuous than the chain of ponds, but more sinuous than the meandering river. Okay, meander wavelength. Let's go back and measure that quickly. So there's a couple of areas where we could do this, but let's just do it. We'll do it in 3 spots just to get a little estimate. So the first one we'll do is from here to here. So that's 1,480 meters. I'll just do, because we've asked for it in meters, 1,480 meters between those two meanders. We can also do it between this meander bend. Clear that, start again. That meander bend and that meander bend. That is 1,150 meters, 1,150. And we'll do it once more, maybe zoom in a bit. They're not very big bends. Whoops, clear that. They're not big bends, but we'll do it from there to there. That is 1,030. So what I'm going to do is not calculate an average of the meander wavelength here, because you can see an average is not particularly meaningful. This is quite meandering. This is not so much. That's almost dead straight. That's almost dead straight. What we'll present here is a range. So go back to our worksheets. The range of meander wavelength here, it's a range from 1,030 to 1,480 meters. So giving a range like that is fine because, well, as you know, the average that you calculate may never occur in the real world. But by providing a range, you're saying I measured a few things, here's the minimum, here's the maximum. Okay, indicators of channel instability. Well, really the only indicators of channel instability in this system are the meander bends moving around a little bit. So let's go back to Google Earth quickly. There is a tiny bit of point bar development here on the bend, a little bit of development of that point bar, and there are maybe some old channels, in this floodplain. It's hard to tell. Maybe the channel used to come straight through there, but otherwise it's not doing a lot. I mean, it is bouncing from side to side, but we don't have a lot of evidence of the channel moving around. So really the only thing this channel could do is move its meander bends around a little bit. So we'll go back to the worksheets and just fill this in. Okay, so meander bend movement, and that can take a range of different forms. It could be migration, which means movement sideways. It could be translation, which is movement downstream. Or what's the other option? There's really not that many options, to be honest. Yeah, let's just leave it at those. They can move sideways, they could move downstream. So what planform type is it? Again, this is a partly confined alluvial meandering river. And if you want to go nuts with discontinuous floodplain pockets.
No.
Okay, so you give me a bit more detail of that planform type. All right, let's go. Let's just do one more and then I'll give you 5 minutes to go and have a look at the others. Hopefully the other meandering rivers, you can measure their meander wavelengths and their sinuosity the same way. It should be reasonably straightforward, but I'll go to one of the crazy ones, which is number 8. Let's go look at the anastomosing river. So let's go back to Google Earth. All right, let's go to site number 8. So, well, on our way to site number 8, let's just go have a look at very briefly these other river types. So this is the sand bed meandering river that was in Gippsland. You can see the sand in the bottom of the channel. Yeah. You can see the old channels out on the floodplain around it. So this thing can move sideways, it can avulse, it can do lots of different things. It can shift its thalweg around within the channel. And obviously calculating the sinuosity here, it's pretty easy. You follow the channel down. You can then go straight down the valley. Meander wavelength, you can calculate the distance between these meanders. You can pick a couple of others. So that one should be pretty straightforward. This is the Wandering Gravel Bed River. Sorry, I didn't mean to go back to New Zealand. The Wandering Gravel Bed River, again, you can do the same thing. Trace the channel look at the valley length just in a small reach around the channel to calculate those different things. Back to the Murray River, the fine-grained meandering system is really beautiful. There's a large range of different meanders here that you can measure. So the meander wavelength here is very different to here. There is different to there. Beautiful little horseshoe-shaped one here. And if you go further downstream, there's some really nice regular meanders just in that little stretch. Good for calculations. You can see this is a much more sinuous river. If you were to, and let me just show you quickly, if I was to draw a line where the river goes, and you were to calculate the distance of that versus the straight line distance of that valley, you can see that the sinuosity number here is going to be much, much higher. But let's go into Central Australia. This is the sort of area that I do my research, and the channels become a little crazy. So, question for you here is, what the hell are we looking at? This is an anastomosing river. It's a fine-grained anabranching river. And these are all channels that you're looking at. They're not braids, okay? So if we zoom out a little bit, you can see the floodplain. There's sand dunes over here being blown onto the floodplain, blown around. You can see some bedrock. So the floodplain is this whole light brown area. The channels are a little bit darker, mainly because they've got vegetation around them and a bit of mud. You can see some really beautiful large water holes sitting around. There's a couple of other longer ones just dropped in the middle of the floodplain here. It's dry. Where was that? Here's a water hole. Just sitting there full of water with a few channels joining up to it. You can see that some channels are very sinuous and others are dead straight. So here for sinuosity, you might want to present a range of values, basically from 1, dead straight, to quite sinuous, maybe 1.5 or 1.6 for this one. Why am I saying that these are all channels, not braids? Well, if you have a look at them, they've all got, I think this is one of the areas with the good imagery. It's all right. Hang on. The imagery sort of comes and goes. There are some bits with really neat, great quality imagery. Here we go. So you zoom in on these, beautiful imagery. You can see that these channels, even though they're next to each other, each one has a clearly defined bed and banks with vegetation growing on it. And here's the next one, and here's the next one, bit of a water hole, that one. Here's the next one. Even this one that's pretty discontinuous, you can see the channel trace there. Well, that's the crappy imagery over there. And importantly, what we're looking at here is channels that are separated by sections of the floodplain, not loose, easily movable bars like in the braided river, okay? So this is floodplain that separates the anabranches here. It's why this is an anabranching or anastomosing river. Like I said, anastomosing rivers are just the fine-grained versions anastomosing rivers are fine-grained anabranching rivers. So this is a really neat example of, beautifully defined, clear channels occurring one by one next to each other across the floodplain. So let's have a look then at the rest of that table. Indicators of stability and instability, all those sorts of things, keeping that image in your head. Let's just fill this out. So how many channels? Let's just have a little joke here. I will mark you correct if you write too many. Don't try and count them all. There are too many to count, but there are many, many, many channels in that particular anastomosing system. Sinuosity will range from 1 to roughly 1.6 or maybe even more, depends on what channels you measure. Meander wavelength will vary greatly as well, but if we go and have a quick look, what you'll see are that these are very small meander bends. So let's go find one of the sinuous systems. Yeah, this one will do. Where was that other one that was better? Yeah, this one's quite good. So let's just calculate meander wavelength on this sinuous one. Obviously, in these other, you're going to have a range of meander wavelengths here as well, but I'll just use my measuring tool here. Let's look at the distance from there to there. That's 240 metres. The distance from here to here is 170 metres. Let's go downstream here to here, 270 metres. So the range, just for that one channel, the range is something like 170 to 270 metres. Very, very different from the 1 kilometre meander wavelength of the partly confined river that we looked at. In terms of channel instability, what are we looking for? Well, this thing doesn't have a lot. So actually the channels are very stable. So it has fine sediment which stabilises the channels. You can just write stable channels if you like. Plus vegetation which stabilises the channels. And if there are indicators of instability, it's that avulsion. So I'll put that one in bold. That's the main form of channel adjustment, which you can add that back up to the table above, avulsion. Avulsion, so channel jumping from one spot to another spot is the main form of adjustment and the only evidence of these channels being unstable. You can imagine for that big anastomosing river, when a big flood comes, and you've probably seen this in the news, Cooper Creek or the Diamantina River, when they flood, water immediately leaves the channel and goes everywhere. So the channels don't actually change a lot during those big floods. They just sit there underwater waiting for the flood to disperse. What planform type is this? As we said, it's an unconfined alluvial anastomosing river. All right, so in terms of planform type, we're really just wrapping together a few different terms here. Multiple channels, unconfined, they can modify their bed and banks. That's what we're saying. So do you want me to leave you for 5 minutes to have a go at the rest, or shall we move on to the next part of the prac? Give me a thumbs up if you'd like to give you 5 minutes just to go do the others quickly, or a thumbs down if you don't want to do that and you'd rather just move on to the flood hydrology one. I'm just mindful of the time, but also want to give you a chance to, to do your thing. Nick says move on. Thumbs up for moving on if you're happy, if you understand the principle of that. Can't find the thumbs down. Keep going, says Mike. Good one.
Happy to move on.
Happy to move on? Good one. Yeah, sorry, I don't know where the thumbs down is either, but I'm glad it's turned off. Otherwise, I'd be getting them all the time, I reckon. Alexander, thumbs up. Good. Yeah, so thumbs up only, really, from here on. That's good old Zoom. It only lets positive feedback, all right? All right, well, let's move on then. Second part of the practice. This is going to get a little bit more hectic. We're not just browsing the world with Google anymore. We are actually going to do some calculations here, and it might do your head in a little bit, but we'll move through it carefully, and you should be fine. So, in your worksheets, you've got the tables, you've got the formulas that we need to use, and we've got some questions. But I've actually replicated all of those for you in the Excel spreadsheet. So let's go to the Excel spreadsheet where you will see all of this stuff. So open it up for yourselves there. All right, I'm just going to zoom in on mine and I can share the screen with you if you like. All right, so we'll get to the calculations in a moment. I'll talk you through those. It's not just about dropping you in the deep end, don't worry. Okay, so what are we doing here with this part of the PRACT? Well, if you've got your spreadsheet open, what you can see is that we have a range of data there for one river, the Squamish River in Canada. This is an example that we're using. We've been using it for many years. It doesn't matter which river you use, to be honest, but Gary Briley, who's one of our old professors, now lives and works in New Zealand. He worked for many years on the Squamish River, and he designed this PRACT years ago, and this river was close to his heart, so he used its data. It's really the only reason we're using it. But the reason we're looking at this sort of data is because the amount of water that a river can move and the energy, that's the next part of the PRACT, the energy at which that water moves through a system, it really is fundamental, as we've just seen, in determining how that river looks, how it behaves, and the valley setting and climate really drives how much water is available to a river and how quickly it moves. So we've already talked about valley settings, confined valleys can really punch water through. The channels are quite straight. They're very energetic. They can move gravel, that sort of thing. And at the other end of the spectrum, those anastomosing rivers have very, very wide, broad floodplains. They're generally very low energy. They can only move mud and clay around. There's no gravel in them. And the channels are generally very stable until they avulse or flip around. So they're the sort of two ends of the spectrum. So a plot of discharge over time, so that's flow in the river over the time, is called a hydrograph. And you can measure flow with a handheld meter. You can do it with gauges. I mean, it doesn't really matter how, but the information that we get is normally expressed in terms of discharge in cubic meters per second, that water. So you can imagine a cubic meter, that's a box 1 by 1 by 1 meter size. When we talk about a discharge of 700 cubic meters per second, it means 700 of those boxes moving through a river channel per second. And that's a lot of water, if you imagine that. So some rivers have very high discharge, other rivers have very low discharge. Some rivers have high discharge all the time. Other rivers have discharge that's, of any description once in 10 years, and the rest of the time they sit there dry. So these rivers are all very different. The reason we look at discharge is because we can use a flood record to reconstruct key elements of that river's, either its history or to predict what might happen in the future. So what we're going to do here is look at this discharge data over time. We're going to basically do what's called Gumbel analysis. It's basically fitting a trend line to this discharge data set in order to estimate some key parameters for this data. So the first thing we're going to do is calculate the rank and recurrence interval of these different floods. So let me share my screen with you. I'll share the spreadsheet. Okay, so over on the left here, I'll just zoom right in. We have the rank and recurrence interval of these different floods. At the moment, the flood data is arranged by date. So what we have here is the peak annual flood for these years. That means the largest flood on record for that year. The date is obviously related to the day that flood occurred. And you'll see that 1955, 56, 57, 58, 59, there's one record for each year, different months, different days, but one record for each year. It's the largest flood that year. What we want to do is sort this data by the size of the flood, by the discharge. So the first thing to do is, we don't have to select these blank columns, to be honest. Let's just sort by date and discharge. So let's just choose all that data. Now what we want to do up in the top is sort and filter. Let's do a custom sort. We want to sort by discharge. You can see it's found that the column has headings. we want to base it on the cell value, not their color or, how nice they look or they feel. And we want the order to be from largest to smallest. So go OK, and all of a sudden, because we've selected both columns, it's also sorted based on the discharge to date. We can now see that the largest discharge on record down to the smallest discharge on record is ranked for us. 1984 had the largest discharge, 1977 had the lowest discharge, and now we can add a rank. So this is obviously number 1. Next one's number 2, next one's number 3, and so on. If you don't know this little trick, once you've got a series here spelt out, you need at least 3 of them in a series, you can hover over that bottom corner, double click, and it will extend the numbers down to the bottom. If that series was in 2s, so let me just do this for 2, 4, 6, and I'll just delete the rest of those. If our series is going up in 2s, Excel will recognize that and it will do the rest in 2s as well. So you can do this for any data set. Let's just go back to the rankings from 1 to 33. Everybody done that? Can I get some thumbs up if you have done that and it's all looking okay? Excellent. All right, so now using this equation, I've copied and pasted the equation there for you. We want to calculate the recurrence interval. So the equation there is the total number of years with records. So here we have 33 years of records, plus 1, divided by the rank of that particular flood event. So why do we add 1? Well, if we used just the year of record, one of these would have a value of 0 once we divided it by itself. So we don't want that. We want the total number of years plus 1 divided by the rank of that event. So up here we can type a little formula. If you want to be really strict about it, you could go 33 plus 1. I think we all know what the answer to that is. Divided by the rank. And press enter. So 34. The other way you could write that formula out is just equals 34 divided by the rank. Either way, we can now double click and populate that formula. Oh look, my graph just created itself because I'd already made it. There you go. You can do this. We'll make this graph in a moment. Okay, so what we've done there is it's the same formula, 34 divided by that particular rank. The way to interpret this data, obviously this flood is the largest flood. It's ranked number 1. How many times did that flood occur in all of these years, guys? Multiple times or only once? Give me a thumbs up for only once. So yeah, we've got something on the chat here. Yep, Billy, once, exactly. Laura, 1. Beautiful. Yep. So its recurrence interval for this data set is 1 in 34 years. Yeah? So that's why its recurrence interval is 34 years. It's only happened once, and based on the data we've got, it's likely to only occur once in a period like this. At the other end of the spectrum, this flood is the smallest flood. How many times was it? It's ranked number 33, but how many times did this flood or larger occur in this data set? Every time, right? Every other flood is larger than this low one. So it means that its recurrence interval is 1. That means it occurs every year in 34 years. Does that make sense? Give me a thumbs up if that makes sense. So a recurrence interval of 1 means it recurs every year, 1. Because every other flood exceeded it. It got to this level and then kept going. If we look somewhere in the middle, well, here's one exactly, with a recurrence interval of 2, it's not double the lowest flood or half the largest flood, but statistically speaking, that flood level was achieved every second year. Or so it occurs every 2 years. Yeah, thumbs up. Anyway, basically this is just a way of understanding, once we've ranked our data, to understand in statistical terms how likely it would be that that flood, based on our data, would reoccur in that system. You can do this for any river, doesn't matter which river. Okay, so now what the hell does that mean in terms of predicting something else? Well, what I would like you to do is create a graph, and we can do this from scratch, so sorry for the deleting the answer there. Let's make a graph, and what we want to do is graph discharge. So let's take recurrence interval and discharge. We want to plot those against each other. We want to insert a scatter plot, so not a line graph, always a scatter plot, and not connected by lines. We don't want that one, we just want a raw scatter like that. As always, Excel is useless and it doesn't know. Can you see that on my screen? It's put these on the wrong axes. So what I would like, so you can add a title up here, Squamish River Flood Analysis. We need to swap this data around though before we do much else. What it's got here is it's got discharge, these big numbers up to thousands on the x-axis, and it's got the recurrence interval on the y-axis. We want to swap those around. So right click on the data set, select the data. You'll then get a box pop up. We want to edit this first series because that's the only series we've got on the graph. And what we want to do here is select the x values. We want them to be along the bottom. We want that to be the recurrence interval. So you probably have to delete this, and we want to select recurrence interval as the x value, and then the y values we want to select discharge. And then you can press OK and OK, and now it looks a bit funky again, but it's flipped our axes around there. So now what we can do is add some axis titles. This is discharge in meters cubed per second, and actually it's peak discharge in QMEX, meters cubed per second. This one is recurrence interval in years. We don't need the decimal places, but you know, I don't really care if you've left them on there. If you right click, you can format the axis, and over on the side here it gives you the number, decimal places, 0, go away, we don't need you. Alright, so let me just move that, yep, okay. Alright, so now what we want to do is view this as a linear trend. I mean, this is a logarithmic, basically a logarithmic curve here. But you can see we've got one flood on record that was huge, with a low recurrence interval right out here by itself. We've got a big gap here between these floods, and then we've got a lot of small floods. A lot of the floods that occur regularly are down in this end of the chart. So one way of looking at this data would be to change the scale of the recurrence interval axis, the x-axis, because this is where the largest gap occurs. We can change that to a logarithmic scale. So if we format the axis and then over here on the right choose log scale, it changes this graph now. It looks a bit more like a straight line. The gaps have shortened in. And in Gumbel analysis, because it's easier to sort of draw trends, especially if you're going to do this manually by hand, it's easier to draw a straight line trend through this with a ruler than it would be to, if I just undo that, than it would be to draw a trend through this with a curve manually. Back in the day, Gumbel analysis was always done using a log scale so that they could draw a straight line through the curve. In Excel now, you can just choose to fit a trend of any description and it works. So It doesn't really matter, but for historical sake, we're going to leave it on this log axis. Now, that's a log-base 10 axis, which means it's showing intervals 10 apart. If we just change that to a log-base 2 axis, it's still log axis, but it's showing the intervals only 2 apart. Well, it's doubling, but 1, 2, 4, 8, 16, 32. It's doubling it, okay? So we've just changed the way we're displaying that axis. We're not changing the data at all. And so now we're ready to fit a trend line to this data set. Give me a thumbs up if everybody's happy with that. Have you got to that point? Or shout out if you've got any questions. I can't see the chat, unfortunately, but...
Can you tell us how to change the axis again at the start, please?
Yeah, sure thing. Change the axis. So we're going to make it into a log scale. What you need to do is right-click on the axis, so down the bottom here, right-click, and then format the axis. And you'll get this box. I've already got it popped up over on the right here, format axis box. And then down, about halfway down, we've got logarithmic scale. So you can turn that on or off as you like. Yep.
And just flipping it, sorry, I'm still on that.
That's all right.
So how do you change the, didn't you change X and Y?
Oh, sorry, to flip the data set from one to the other?
Yeah.
Yeah, sorry. Yep, that's different. So you need to click on the data set here or the graph. You need to go to the select data option. So you can click on the graph or anywhere on the data set, select data. Series 1, that's the only one here. I haven't given it a name, which is why it's got this just a random name. You could call it recurrence interval, you could call it Squamish River, whatever you like. But we need to edit that data series. And now here in these columns is where you specify. So I've got the x-axis values as the recurrence interval here in column D. I've selected all of those. So it's giving you the range D5 to D37. Hit enter. And then the y values, I've got the range B5. So that's the discharge values, B5 to B37. Hit enter. So when you automatically do it in Excel, it puts them the other way around just because of the order that we have the columns in. Anyway, we hit OK, and then it should flip them. So you'll have recurrence interval on the x-axis, which is across, and peak discharge on the y-axis, which goes up.
Cool. Mine's just opposite yours for some reason.
You mean recurrence intervals on the y-axis?
No, that's correct. But the points are going, they're descending left to right, whereas yours ascending left to right.
Oh, okay. You may have, I don't know if this works, on some of the axes, so if you were playing with the recurrence interval axis, next to the log option, so if I format the axis, next to the log scale is having the values in the reverse order. Does it look like that?
Maybe I hit that, yeah.
If you accidentally click values in the reverse order, it'll flip it around like that. So I'm not sure exactly what yours looks like, but make sure you don't have the values in reverse order, and only the bottom axis should be in log scale. If you do log both axes, it goes all funky again. So just the bottom one, and everything else should be all right. Well, what we want to do now is add a trend line, and there's the best way you can add here up on the top. You can add a chart element, a trend line, or again you can right-click, add a trend line, whatever you like. Now, it automatically adds a linear trend line, which because we've made this axis logarithmic down the bottom, it looks funky. It doesn't look straight. If we go back to this axis and change that back to a linear axis, it still won't look good because the trend line is straight, but the data set is not linear. You see this? So I've changed the bottom axis back to linear, So we've got linear axes both sides. Our data set is not linear. So a linear trend line is not what we want to add here. We need to format this trend line. So if I go into the formatting options, you can see on the right here, just click on the trend line. Over on the right here, there's a few different trend lines we can use. Try a few of these. I'll just leave mine as a linear axis down here, but when you're doing it with a logarithmic axis, that might give you a hint as to what sort of trend line we need. You can look at the shape. If we try exponential, well, that's even worse. We try polynomial. It's getting a bit crazy. Let's try logarithmic. Okay, so on my linear axis, a logarithmic curve seems to fit pretty well. And if we then go back to this axis, and I'll just display the equation and the r squared on the chart. We want to always show those whenever you put a trend line in. I'm going to go back and just change this axis back to its log scale, and suddenly this looks nice and sensible. Everybody able to do that? Give me a thumbs up if that's all right. It's a bit of clicking around here, but we'll get there. Nick, the thumbs up, good work. Sorry, I can't see you all at once. If people are down the list giving thumbs up, then that's good too. All right. So once we've got that trend line, what we're going to do is now do a little bit of analysis. So now that we've done this, what we're doing by adding a trend line like this is saying that, you know, even though we've got gaps in our data set, this line best approximates discharge and recurrence relationship in this river. So we don't have, if you look at discharge of 2,500 cumex, we don't have a record in this 34 years of discharge being 2,500. It wasn't measured exactly at 2.5. It was measured at 2,600, but it didn't peak at 2.5. So we've got no data point there, but our trend line runs through that part of the graph, of course, which means that if we want to know how often a flood of discharge at 2,500 would likely to be recurrent, we can come across to that part of the graph, and I'll just do it manually here. This is the sort of thing we used to do with a pen and paper back in the day. If you said, well, what's the likelihood of having a flood of discharge 2,500? How do we determine that recurrence interval? Well, we need to draw another line down. It will come down to here somewhere. Just make it red too. So that's the sort of question we're asking. What's the recurrence interval of a flood of peak discharge 2,500 cumex? Well, you have to use the trend line to estimate that. And in this case, it's hard to tell on this little graph, but if this is a log scale, it's somewhere in the order of probably 20 years or 25 years recurrence interval. But we can actually use this equation for this line to solve that problem exactly. So what we're going to do is answer a couple of questions up here, and they're in your spreadsheet, so go and have a look at those. The first one is just go across again. You can see the answers there, but let me just delete them for you. What is the magnitude of the mean annual flood? That means so that the mean annual flood is a term. It's a statistical term, and also statistical bankfull discharge. That's a statistical term, a river's term. What we're asking here is, what is the magnitude of the mean annual flood? That means, what is discharge when the recurrence interval equals 1.58? So the definition of the mean annual flood is a flood recurrence of 1.58 years. So what are we going to do? We're going to take this equation over here. We're going to copy it. We're going to paste it in this little box, which at the moment makes no sense at all because it's not live. But we want to solve, so this equation is, remember, y equals all of that. That's our equation of that trend line. We're going to now solve this equation Y, if you remember, Y is discharge. It's on the y-axis. X is recurrence interval on the x-axis. So we're going to solve this equation to calculate Y, which is the discharge. So what we have to do is substitute for X. We need that to be 1.58 because we're asking, when the recurrence interval is 1.58, what is the discharge? We then need to fiddle with this a little bit more. We want to get rid of Y there because we want to make this cell. This cell is now Y. This cell is equal to 557 times the natural log of 1.58 plus 726.28. Now, 726.28, that is the y-intercept value where this trend line crosses the y-axis, okay? So if you just get that equation into your cell and press enter, you should get the answer. Discharge, so what we've said here, it's the opposite to what I drew up here. What we've said is if X equals 1.58, which is roughly, there, we've said what is the discharge at that level. And we've generated, using the equation of the line, we've generated the answer for that point on the axis. It's 981. I don't care whether you use 1 or 2 decimal places. Certainly don't put them all in your answer sheet. But that's basically what you need to do. Thumbs up for that one. Does that make sense? How we're solving this equation using the X value to find Y, which is discharge? Yep. So you can do that yourself. This is pretty simple. Now for B, we now want to know what the statistical bankful discharge would be. That is, what's discharge when the recurrence interval is 2.33. So we want to solve the same equation now, but instead of, so if I just copy that and paste it, we now want to swap out the X value in that log box for 2.33 and solve it again. Now it equals 1197.7. So what we've said, if I zoom over to the graph here, we've said when the recurrence interval is 2.33, what's the discharge? Okay? We're solving this equation. Now the last one, and I'm going to leave you, there's the answer there. I'll just delete the formula. This is something for you to do in your own time. It will take a little bit of work, and you may or may not get it right, but don't worry, this is not worth a lot. It's worth 1 mark out of 30 for this whole PRACT, so don't worry too much about it. A little exercise for you is to go and do the reverse calculation from this. So remember, we have our equation here. I'll just copy it and paste it here. That's our equation. And we just solved it in the way that it was written by substituting an X value. Now we want to find out X. We don't want Y equals this, we want X equals this, which means you have to rearrange this equation and substitute the Y value. What we're substituting for Y is 3,000. Okay, we're saying how often would a flood of magnitude 3,000 QMEX occur? So what is the recurrence interval at discharge of 3,000? You can see here that 3,000 is off our chart. It's beyond anything this data set has ever seen. But you can, there's a bit of a tool here with the trend line. You can forecast the trend line forward. Let's take it forward by 500. Basically, that was 500 periods. Whoops. I basically just want to extend the trend line past 3,000. It's not changing any of the data, but it's just taking the trend out. So what we are now saying, just like the first example I gave you, was, okay, if discharge is 3,000, what's the recurrence interval of that flood likely to be? So we're going to solve it now to calculate X. So this is a job for your homework. Have a crack at trying to solve that equation for x. Basically what you have to do is move all these things. So if you've added 726 to this side of the equation, you need to subtract it from the other side. If we multiplied by, remember this is a multiplication, if we multiplied by 557, we need to divide by 557. If this is the log, we want the exponential, the opposite, 1 over. Okay? So start with your exponential. So instead of a log, we want to bring it over this side. We want it to be the exponential. We want to divide it by 557 minus 726, and we should get what we're left with x. All right? So I'll let you have a go at that in your own time. But the point here is that you can see how a data set like this is really useful. This is a very high energy river. All of these discharges are quite high. But if you wanted to predict how often a really big flood would occur, this is the way you would do it. If you wanted to fill a gap in your data set and okay, well, what's a 1 in 10 year flood here? Well, we would solve, so we could just solve, I'll resolve one of these equations. What's the 1 in 10 year flood? It's about a 2,000 cubic flood. The 1 in 10 year flood event is a 2,000 cubic flood for this system. Okay? So let's move on to the next question. That's all the flood recurrence stuff we're going to do. I'll leave you to rearrange that equation and have a crack. Like I said, it's only worth 1 mark, so not a crisis if you don't get it right, but something you can think about. Let's go. So the next question is all about. For the worksheets, copy and paste your graph in. That's worth a few marks, and answer those 3 questions. They're worth a few marks, and copy and paste the rank and the recurrence interval data into the table. That's worth a couple of marks. All right. Let's go back to the worksheets. Okay, can you see the worksheets there? So I'm looking at now Part C, stream power analysis at a cross-section. Everybody happy for this? We're moving through reasonably quickly. Okay, so this part of the PRACT is about understanding what energy comes with discharge in a river. And the reason we're interested in stream power is that that is a measure of how much work the river can do. So a very low energy river doesn't do a lot of work. It doesn't push a lot of sediment. It doesn't move its bed and banks around much. A very high energy river will do both of those things a lot. So total stream power is the total amount of energy available for a river to work. But you can imagine in a scenario where a flood occurs, when all of the floodwater is within a channel, there's a lot of work happening within the channel. When all the floodwater spills out of the channel and goes across the floodplain, there's still a fair bit of work going on in the channel, but a lot of the energy is spread now across the floodplain. The water is being spread around much further than just in the channel. And so a second measure of stream power that we use, not just total stream power, is called unit stream power. And this is the stream power that works just within a channel. Basically, the reason this is important is because during floods, as I said, water is spread everywhere, and so the unit stream power in a channel sometimes declines. Even though the total stream power goes up, the unit stream power declines in a channel during a big flood. And we're going to look at some examples of this now in these in this next little section. So the equations are simple. We're not solving crazy equations just like we did then. The equation for total stream power is given to you there. It's when, I'll just zoom in a little bit. Can you see that on my screen? It's when, so total stream power is the specific weight of water, which doesn't change. That's gravity times the molecular weight of water, 9,800 newtons per cubic metre. So that's always the same, multiplied by the discharge, multiplied by the channel slope. That gives you total stream power. And the way we calculate unit stream power is to divide the total stream power by the width of the channel. So what we're saying now is if you had all of that energy focused into the channel, give us the number. So what we're going to do in this section is look at this transect of the Bega River. And what you can see here are the flood recurrence intervals. So remember we just talked about them, the 2-year flood, the 5-year flood, the 10-year, the 50, the 100-year flood levels for the Bega River. And what you can see is the 2-year flood event down the bottom here. Let me see if I can just put a circle around it. It's a bit hard to insert a shape, make it a circle, and unfill it. Sorry, this is all very clunky. Okay, so there the 2-year flood event on the graph the water does not get out of the channel. It's all sitting in the channel there. Similarly, the 5-year flood event just above it is still sitting in the channel, but it is inundating that little bench in there. It doesn't get up to the banks though. If we look over here at the 10-year flood interval, flood water now is suddenly out of the channel and right across the valley. It extends all the way across the valley. And for the 50 and 100-year events, it just gets higher and higher and higher. So for each of those flood events, what we've given you here is the flood return period and an equation which reflects the catchment area to discharge relationship for that particular flood event. So it is the solution to a line, but not the same as the one we just plotted up. What we're going to try and solve this for initially is, again, to calculate the discharge for each of these flood recurrence intervals. And what we need to substitute in here as x is the catchment area. Now, I've just realised that should say catchment area, which is x, to discharge relationship. Discharge is y. So down in the table below, you've got the catchment area is the same for all of them, 85 square kilometres. So what you need to do in your spreadsheet is substitute 85 for x and then solve each one of those equations. It's quite straightforward. Let me go to the spreadsheet and I'll go to the discharge and stream power. So on the second tab, I'll just delete the answers. Sorry about that, guys. On the second tab, you've got discharge and stream power. So what we're trying to do here for this catchment area discharge relationship, and I've copied and pasted them here for you. For this first one, we want to say this equals 0.3706 times by 85, because that's the catchment area. Doesn't change. You could also, if you want to put here in brackets 85, you actually use the cell, you can do that. We need to add a multiplication in there, so 0.3 times 85 plus 28.017. Okay, so we've solved that, and that equals 59. So now you need to repeat that for each of these other different equations. I'll just let you do that for a second. You can just type that out, okay? Just stop sharing for a second so you can just type that out. Okay, were you as quick as me? No. So type each of those out. 85, you just substitute 85 for x in all of those. So you just need to type out those numbers, times 85 plus the y-intercept, and there you go. Now, what I've given you in that document is a set of graphs that should automatically populate. So once you've filled in these discharge numbers, you'll get the discharge shown to you to your event, 5-year, 10-year, 50-year, 100-year event. And you can see they just go up and up and up in terms of discharge. There's not much change. It's a linear sort of trend. But the story is quite different when we look at stream power. So the next thing we need to do is calculate total stream power. I'll just show you the equation for the first one and then you can do the rest. So total stream power, if you remember, we said it was the specific weight of water times discharge times the slope. So we've got the slope here in the channel. It's the same for all of these measurements. So really what we need to do is multiply the discharge, like we had, by the slope by 9,800, which is the specific weight of water. And once you've done that, the formula is the same. You can drag and drop or double click and populate that formula right through the data set. And again, here in your graphs, you'll see total stream power chart. It just goes up and up and up. It's basically total stream power is directly proportional to discharge because slope and gradient is the slope and specific weight of water aren't changing. So it's really just a reflection of discharge. Give me a thumbs up when you've got those two columns complete. Sorry, I just saw a chat pop up, but I can't actually see it. I'm trying to find it. Where's the chat?
Because I'm sharing again for the second column.
What was that, sorry?
The formula again for the second column.
For total stream power? Yep. So for me, you can look at the cell values there. It's discharge times slope times the specific weight of water. So in your PRACT notes, it's written out as well.
Hey, sorry, this might be a silly question. But I just see the equation for the first one for the discharge because I feel like I'm putting it in correctly, but I'm getting a funky number. And I'm not. I'm following the PRACT.
Yeah, that's cool. So we want, it doesn't matter too much where you put your brackets, or you don't actually need brackets at all because it'll do the multiplication first. So I can even take these brackets out. It should be 0.3706 times 85 plus 28 gives you 59. I just put the brackets in because it then separates out that part of the equation from the addition of 28. That's when you've got a hectic equation. It's definitely worth putting the brackets in. This is not too bad.
Cool.
And for each of the others, it will be a different number. So it's 1.38 for the 5-year flood. It's this equation, 1.3861 times 85 plus 62 in that case. So each of those will be different.
I was using the cell. I was selecting the cell, but for some reason it was giving me 49. But then when I retyped the actual number, so I don't know if
you were using that cell, like B times B5 or something?
Yeah. I might try it again. Maybe I've just toggled something correctly.
Yep, that's okay. So once you've got the discharge values, even if for now, if you do the first one, the others you can just type in. Stream power is a very quick calculation. Once you've done the first one, you can drag and drop that formula right down. That's easy. And then unit stream power is just the total stream power divided by the width of the channel. Now remember, channel width, if we just go back to our cross-section for a moment, or you go back to it and have a glance, remember the 2 and 5 year flood events were both contained within the channel. And so they have very small, relatively small channel width, 60 metres, 75 metres. But the 10-year, 50-year, and 100-year events were out of the channel. They covered the whole valley, which was more than a kilometre wide. And so this unit stream power metric becomes the really interesting one. If we look at that formula, so it's just total stream power divided by the channel width, and then drag that down, we get some numbers. That's all great. The really interesting thing is we start off at about 28, we go to 70, and then we drop dramatically down to 7, and then 13, and then 18. So even though these really big floods have a lot more discharge and a lot more stream power, on the whole, the unit stream power, so their ability to do work per square metre, is lower. And if we have a look at the graphs down here, you can see that while discharge was pretty linear, total stream power pretty linear, when we take into account the channel width, this is not a linear trend anymore. Bigger floods do not equal bigger unit stream power values. And the reason, this is one of the questions you need to answer that I'll leave you to answer. I'll talk to you about it now, but you can write some words around it. Why don't we get that sort of linear trend? It's because the energy is being spread over the whole floodplain for the 10 and 50 and 100-year events. They have lower energy per square metre because there are many more square metres of floodplain being inundated by the same amount of water. Well, it's more water, but it's spreading energy all over the place. Does that make sense? Can I get a couple of thumbs ups if that's making sense? Sorry, Mike, did I miss, or maybe you shouted out, can you show the formula again? Sorry.
All good.
The chat has now popped up miraculously. Sorry about that.
All good. Thanks, Tim.
But yeah, just shout out with a verbal question if you've got one. So I'll zoom out again. This is what you should end up with, a table that's full of numbers. You can translate those back into your worksheets to hand in. You'll have a couple of graphs. You don't need to repeat these graphs or paste them in, but these will help you answer the questions that I've asked. So the questions in the spreadsheet, in the worksheet, please explain the unit stream power trend. That's the unit stream power trend at the cross section. So that's this bottom graph. What happens? We basically get a great increase up to the 5-year event, but then when the water goes over the banks, the unit stream power declines dramatically. So you want to spell that out in a little bit more detail, only a couple of sentences, but a little bit more than I just gave you. And then the second question is, okay, theoretically, if channel adjustment can occur at a unit stream power of 30 watts per square metre, that's that red line I've drawn for you there on the unit stream power graph. So if channel adjustment can occur if a flood exceeds that, do any of these flood scenarios, will any of them lead to channel adjustment? Anyone want to pipe up with which one might lead to channel adjustment? Just looking at that graph. It's not a trick question. There's only one that goes above 30, right?
5-year, yeah.
The 5-year event, yep. So based on this data set, only the 5-year flood event is likely to have channel adjustment occurring because it's got enough energy within the channel at that point to move the bed and banks around a lot. The second part of the question is, there's a threshold estimated for stripping of the floodplain. That means removal of all of the floodplain sediment at 300 watts per square metre. Would that occur under any of these flood events? And the short answer is no. Watts per square metre, the axis for unit stream power is over here. We only get up to 78 with all of these flood events. And actually the 100-year flood event, which goes out onto the floodplain, only has a unit stream power of 18. So we would need a much, 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 much greater flood than a 1 in 100-year flood to strip the floodplain off, to achieve 300 watts per square metre, which is way off the chart here. So you can have a go at just putting a couple of sentences together to answer those two questions in your own time, okay? And they're worth a mark or two each. Happy to move on to the last the last part of this prac. Got thumbs up from everybody. Is that reasonably good? Yep, thumbs up from Laura, Billy, thank you. Excellent. All right, so the last part of the prac doesn't involve a spreadsheet. Phew. Doesn't involve calculations. Phew. Doesn't involve zooming around the world and Google. Whew. It just involves looking at the long profile of the Bega River that we've given you and describing in basic terms some of the downstream trends that you observe there. So I probably don't need to share my screen with you here. You can look at the long profile trend along the Bega. It's in the PRACT notes. So have a look at that now and we'll just talk through it quickly and then we'll talk about some of the trends. So the top part of the graph has a couple of different things shown on it. The grey shaded data set is the gross stream power. That's the total stream power. And you can see there's a big peak around 10 kilometres. There's another peak around 60 kilometres downstream. On the x-axis is the downstream distance. The other two things shown on that top graph are in the thin black line, the elevation, the long profile of the river, running from left down to the right. And the dark black line is the catchment area, increasing as various tributaries enter this trunk stream. Down below that graph is a schematic diagram of what is going on in this river downstream. So if we just look at the landscape units section first, you can see that we start off in the uplands over on the left. We then go through an escarpment, through rounded foothills, down onto a lowland plain. Can everyone see that? Can I get a thumbs up if you can see that? Yep, good-o. Nick, Marianne, perfect. All right, so if we look then at the schematic valley confinement channel width diagram, what that shows is like a bird's eye view of what the valley's doing in these different areas. So you can see up in the uplands, it's very narrow. There's no grey, which is the floodplain. There's no grey. So it's just a channel in a confined area. It goes through the escarpment. It's very narrow and steep. It then gets into the rounded foothills where the valley widens up a little bit and the floodplain starts to occur. So we've got the channel getting a bit wider and the valley getting wider. And that gradually widens all the way downstream, except there's a little pinch point around 60 kilometres where the channel doesn't get any narrower, but the valley comes right into the edge of the channel. So the valley is now squeezing the channel. It's like a little gorge there. And then in the lowland plain, you can see the channel gets a little bit wider again, but the valley gets very wide. It's completely unconfined there. Everybody happy with that? And then if you keep looking down, you can have a look at the different... Oh, yeah, sorry, go ahead.
Do you mind sharing your screen just to annotate where you're...
Yep.
Where you're to?
Sure, can do. Okay, so I'm on this long profile. Can you see that figure? Can you see my mouse, where my mouse is moving around?
Yeah, that's what I mean. It just sort of follows you.
Yeah, cool. So we started off with this top graph, which shows gross stream power here in this grey shaded data set. The long profile or the elevation is this thin black line, and the catchment area is this jumpy, thick black line. These are where big tributaries enter, bringing in more water. Down below here, we're talking firstly about the landscape unit, so these upland areas. So these notes relate to this part of the graph. This is the upland area. It's got a narrow, confined valley. It's a steep headwater river style, and it's where the source of all sediment comes from, up in here. Then we have this escarpment, which has a gorge in it. Then we move down into these rounded foothills, which has basically this confined valley with occasional floodplain pockets. We've got a really small area here, like a little pinch point that I mentioned, where the valley width comes right in against the channel. And then down here, we've got the valley opening right up in the lowland plain, very wide valley, unconfined, where sediment's being spread around and accumulating. So the question for you here, looking at this graph, is number one, how does the energy, that means the total stream power, how does the energy of this system change in a downstream direction? It's not just a linear change, high stream power to low stream power, although there is a bit of a trend in that direction. The way I would describe this is that it's variable, but, high and then low, high then low, variable up in the upland area, but then dramatically increases at the escarpment, where this steep part of the long profile occurs. It's where by far the highest stream power occurs. And then stream power levels off and it's pretty low for the whole rest of the river, except for a couple of places. Around 60 kilometres, we've got this big peak. Around 35, we've got quite a large peak as well. And what we need to do is sort of look in and figure out, well, why are we getting these little peaks here? The first thing we could do is look at, well, why do we have a big tributary enter where we get these big peaks in flow, energy? And the answer is no. So there's no big tributary there. Catchment area doesn't jump up there. Catchment area doesn't jump up here. It's got major tributaries entering. The Brogo River comes in, but stream power doesn't do much at all in response to that river entering. So catchment area is not really controlling stream power at all. If we zoom in on the long profile, what we can see is that in some places the long profile gets a little bit steeper. So it's sort of hard to tell, but in here it's sort of flat. It goes up a bit, it drops a little bit there, flat. There's a couple of little steps here. So one of the reasons that steam power might be slightly higher in this general area is that the slope of the long profile here is a little bit steeper than it was up in here. So that's pretty flat there. It steepens up a bit and then it becomes quite a bit steeper through here. So low stream power increases a bit, increases a lot. And then when it becomes flat again, we've got low stream power, a couple of steps, high stream power, flat, low stream power, quite a large step there, high stream power, etc. The other thing we can look at, move down, is where this little pinch point occurs, and it pretty much aligns with this stream power, roughly. So it's a combination of factors. We've got high stream power where at the top of the catchment where the slope is very steep. It generally declines through the catchment, but we have periodic areas where it's high, where the river slope increases again. That's the best way to explain that downstream trend. Does that make sense? So I've already talked about catchment area, but the last question is about what external factors control the distribution of energy down this system. And what I suggest is that you just have a think about it, about what I've just been talking about. You can write off tributaries entering. So think back to the valley setting and the slope and the confinement and write a sentence or two about how they are influencing. So it's sort of the detail of what I was just talking about. How does the valley setting as an external control on this river, how is it influencing stream power? Is that all good? So the general trend is that the highest stream power occurs at the escarpment. It's low pretty much everywhere else, but we get a couple of peaks around steep areas. What external controls are most important? Well, it's clearly the elevation and slope of the valley and the confinement of the valley are driving the high energy spots. It's not things like tributaries entering. Okay? So can I get a thumbs up if that makes sense? Good one. So really all you need to do, and you can have a go now. I mean, if I were you, I'd just, while this is all fresh in your head, I'd go back and just make sure you've got all the different parts answered and finished off so that you can submit this without too much extra hassle. I would just go back, make sure you've got the two first tables filled in from the Google Earth, zooming to your best ability. In the flood hydrology section, make sure you fill in the table with the numbers, paste in your graph and answer those three questions based on the calculations we did. In the stream power analysis, fill in the table, and answer the 2 questions about, the trends in stream power and the likelihood of the major, channel change or floodplain stripping occurring. And then in this section, have a crack with a couple of sentences only. Don't write half a page, certainly. A couple of sentences for all these written answers on what are the controls and trends on stream power downstream through a river. And then you can hand in those answers when you're ready. They're due, I think, by Friday, end of the week. So, yeah, no need to rush it, but just make sure you fill it all in and hand it in. Is that all good?
I think it's
thumbs up?
Tuesday on Turnitin, it says. I think the quiz is due Friday.
Oh, okay. Yeah, sure. Yep, Tuesday next week's fine. Yep, I don't really mind.
Cool.
That's all good. I guess it's typically by the day before your next prac, I guess, is what Paul set it up to be. So, yeah, the quiz for this week is due Friday. That should be reasonably straightforward. Make sure you go and listen to the lectures and look at the slides. Yeah, apologies for the recordings from last year. It's a pain in the bum that we have to do it like this, but just ignore all the references to 2019 issues and field trips. All the material is essentially the same. Next week, you'll need to get your brains back into GIS mode. So we're going to be using AppStream, or if you've got GIS installed locally, we'll use GIS locally to start looking at the McDonald River north of Sydney. It's near Wiseman's Ferry. We're going to provide you with a bunch of data on iLearn and a guide for the PRACT. So that'll be up by the end of this week. We're going to start some GIS mapping of the McDonald River, and then over the next couple of weeks refine those maps and do some analysis that will go into your second assignment. So from here on, it's a lot of, in the PRACs anyway, it's a lot of GIS-y type stuff, but all talking about rivers, how we can quantify and measure change using GIS and map them in geomorphic terms. So you'll learn hopefully quite a lot from that. But stay on top of the lectures as well, because a lot of the concepts that we're going to be talking about, just like today, a lot of the concepts, or all of the concepts, are covered in the lectures. So each Monday, get onto the lectures as soon as you can, and then be ready with your GIS ready to go for the PRACs for the next couple of weeks. Okay? Good one. Well, any last questions before we sign off? I can leave the meeting. I can leave you all here to chat if you would like to. Give me a thumbs up if you'd like to stay and chat. I don't have to end the meeting. But otherwise, you can, finish off the sheets yourself. I saw a few thumbs up there. Was that thumbs up yes about next week, or thumbs up yes you'd like to stay and chat? Give me a thumbs up if you'd like to stay and chat. I can leave the meeting going.